Respected Chair, eminent panelist, DG Caps, ladies and gentlemen. First of all, I must thank Caps for inviting me, for giving me this opportunity and to be part of this great cerebral discussion. So I'll start my talk on advanced ceramic and composites for soldier and armor protection. Over the next 15 minutes, I intend to make the case that advanced ceramics and composites are no longer a laboratory curiosity. They are the most consequential material science investment the armed forces can make in this decade. Let's begin with why this matters today. When we talk about advanced ceramics and composites, I want to anchor the discussion not in lab, as I said, but on two battlefields that have defined the past 12 months. Operation Sindoor, May 2025. We all know about this, and what followed in the days after was equally significant for us. The MOD invoked emergency procurement and committed 300 crore rupees for boron carbide bulletproof jackets from Messrs. SMPP because the gap between what soldiers had and what they needed became impossible to ignore. What have we learned from Ukraine, the fragment lesson? The single most important data point, what comes from 3 years of most intense conventional warfare since 1945 is this: 77.5% of combat casualties are from fragments and blast. Not bullets, it is fragments. The ceramic composite armor paradigm built around stopping rifle rounds have been overtaken by events. Wide area coverage now matters more than peak V50 parameter. And India's gap is the Army's cumulative BPJ contract covers roughly, till now what we have procured till now is approximately 2.5 lakh sets. This is the data from the open source. Against a declared requirement of 10 lakh, modern body armor has been shown to reduce fatal torso injuries by over 90%. From the studies of Vietnam, where it was 70% fatality rate in Vietnam War, to under 5% in modern recent conflicts. That means modern body armor is effective. That reduction is what we are leaving on the table. This talk is the material science roadmap to close that gap indigenously. Let me start with what the battlefield actually asks of our armor systems. The soldier's adversary is no longer one-dimensional. The table you see is a threat taxonomy of that spans from drone fragments to kinetic energy penetrators, and the protection technology for each is fundamentally different. At the low end is FBV drones, fragments, grenade, mortar sharpener. A soft armor, yoke, collar, and deltoid protector stops them. This is the dominant threat in Ukraine today. In the middle is rifle armor piercing and hard steel core rounds. This is what our soldiers face on daily basis in J&K CICT. A hard ceramic SAPI. SAPI stands for small arm protective insert, the bulletproof plate what we insert in the jacket. Boron carbide or silicon carbide backed up by UHMWPE defeats this. This UHMWPE, I'll be using this word again and again. This is the backing material, organoplastic behind the plate. The material which is near to the body, between the body and the plate. At the vehicle level, we have 125 mm armor piercing fin stabilized discarding sabot, that is AFPSDS, kinetic energy penetrator, the domain of Kanchan composite or Arjun. At the CBRN end, gamma radiation, chemical agent, tungsten nanoparticle, composites are the frontier response. So what the paradigm shift has taken place from Ukraine lesson is not that we need hard ceramics. It is that we need wider coverage. The average injurious fragments weighs around 0.6 gram to 1.2 gram and travels at the velocity, roughly at the velocity of 1000 feet per second, that is 304 meter per second. That is not an armor piercing problem. It is a coverage problem. And helmet, yoke, groin, deltoid, shin guards can handle this. And we have a unique challenge, dual challenge in fact, and no other army in the world must simultaneously equip for Siachen at minus 40 degrees Celsius and in Thar Desert plus 50 degrees Celsius. That is 90 degree thermal operational span envelope is a design constraint that no foreign BPJ or vehicle armor has been validated against. With the threat defined, let me take you into the physics of how we defeat it and why ceramics and the physics of its defeat of the rounds. There are 4 steps into it. I'll just briefly touch upon them. First is the impact. The ceramic phase with a Vickers hardness of 28 to 34 gigapascal immediately begins to erode the hardened steel core of the projectile. The ceramic is harder than the penetrator. That is the first and foremost critical fact. Erosion. The elastic modulus of boron carbide 360 to 400 gigapascal transits the impulse radially, dispersing kinetic energy in a cone. The projectile nose is blunted and shattered. The third is the fragmentation. Both the projectile and ceramic fragment energy is now distributed across multiple lower mass fragments, traveling at lower velocities. And the arrest, the backing, what I said, UHMWPE or organoplastic backing that catches the fragments cloud and mitigates behind armor blunt trauma that the body will face. Look at the table. Draw your attention to boron carbide. B4C, the third one in the row, hardness of 28 to 34 gigapascal and density of only 2.5 gram per cc. Compared to RHA steel, it is which is approximately 2 gigapascal hardness and 7.8 density. This boron carbide is 14 to 17 times harder than RHA steel and 32% of its weight. Why I'm talking about this is, you'll see in the next slides. That's asymmetry is what makes ceramic composite armor possible at human portable weights. This is why Abhed uses it, and we'll talk about Abhed in the next slides. This is India's ceramic of choice. The last one, the second last is aluminum oxynitride, a transparent ceramic sintered at 1850 degrees Celsius. Bending strength is 255 megapascal, and 19.9 gigapascal is the hardness. And it goes into armored vehicle windows and aircraft canopies without sacrificing ballistic protection. Now, given this physics, how does geometry amplify the material's performance? It is not only the material, but the geometry also affects a lot. Same material, different geometry, dramatically different operational outcome. Architecture is the force multiplier that material science alone cannot provide. The baseline is the layered composite ceramic strike face, organoplastic backing, RHA sandwich, and it is 46 kg per square meter. And the baseline drops to 36.7 kg per square meter when we put a screen. This is modification we are giving to the simple ceramic plate, which means that 20% weight reduction for identical threat defeat, 20% lighter means 20% more mobility, 20% more time before musculoskeletal injury that will degrade the combat effectiveness. Second is the hexagonal cylinder array. That kind of architecture is also possible. Instead of a monolithic tile, a close packed honeycomb of ceramic cylinders. Each cylinder focuses strength on the projectile tip, designed for 12.7 mm HMG defeat, the Dushka and Chinese equivalent of QJ089, the threat on both sides of our active border. Failure of one cylinder will not propagate to the next one. That means it is giving the true multi-hit capability. The third one is the bio-inspired fish scale. There is a study in 2024, and it involves overlapping silicon carbide plus that UHMWPE backing composite scale, biomimicking the fish armor. Finite element method has been validated and flexible. What advantage it gives is the flexible, conformal, multi-hit protection over curved body surface, not available from flat SAPI plate. And the fourth one is ceramic mosaic. The fourth architecture directly answers the question every commander asks, what happens on the second hit? And that is very important to know that a monolithic plate is one structural unit. One round creates a fractured cone that compromises the surrounding area. The second hit in that zone meets a partially defeated material, a mosaic array, breaks that propagation chain. Each tile is bonded through a compliant polymer interface. When one tile fractures, the adjacent tile does not know it happened. Ukraine data shows that 2 to 3 impacts within 100 mm of radius is now a common scenario. Against a monolithic plate, the third impact is effectively unprotected. Against a mosaic array, it is not. India has no indigenized mosaic ceramic array in production or in qualified specifications. The ceramics, boron, and silicon carbides are available. The funded qualification program is not. That is research priority that will be flagged in the last. Let me now move to the textile and soft armor component of the protection system. Hard ceramics stops the bullet, soft armor stops the fragments, and the covers covers where rigid plates cannot move. Look at this chart. The Kevlar at the bottom of 49, it has got value of 232 centinewton per tex. This is the unit which measures, which is used for the fibers to measure their strength. The global baseline for 30 years, the Kevlar we have been hearing in every form. Kevlar 149 is at 295. The Russer C, a Russian third generation high performance aramid fiber at 565. See the difference. That is 2.5 times stronger than standard Kevlar. And let me tell you that DMSRD Kanpur is working in this space. The requirement is to accelerate Indian fiber performance to this benchmark. The architecture matters as much as the fiber. A 90 and 0 degree bidirectional layup is consistently the most effective because fragments arrive from any direction. The fiber network must arrest motion in all directions simultaneously. The matrix material is a procurement decision, not a science decision. Same fiber, same weight. Thermoplastic matrix gives 538 meters per second V50, whereas epoxy gives 391, 38% improvement, and by changing only the binder. That is the specification lever available today. So that means that we have to be very aware about that. The same material, if the specifications and structural changes are made, the improvement can be done in the outcome. One more point, which is very important, the natural fibers. The last card on the right side, and Kenaf and Kevlar hybrid achieves 590 meter per second ballistic limit. And this is homegrown in Maharashtra and Karnataka. Piasawa reaches 272 joules energy absorption. These are not exotic material, they grow in our own country. An untapped indigenous feedstock for armor that warrants a DRDO and academia joint programs. Let me now take you to the frontier, what happens when armor goes to the molecular scale. We have talked about a lot in the first two sessions about nano and nano materials. I'll just touch upon about one material, that is CNT, whose Young's modulus is 7,000 gigapascal. That is the modulus of carbon nanotube, 35 times stiffer than titanium at a fraction of the weight. The theoretical implication is 15 to 35 times reduction in armor thickness. Then manufacturing at scale remains the challenge. India's nanotechnology establishments working in this field is positioned to contribute. A magazine, one material, and 3 functions, which I myself have worked in the field of EM shielding, and it can give structural strength also. The real-time structural health monitoring is also possible through this. So one material, 3 defense functions, direct relevant to command post, shelter construction, and vehicle armor protection electronics. Radiation shielding, tungsten nanoparticle at 50% loading gives 35% higher tensile modulus while providing meaningful gamma attenuation for troops at high altitude or in CBRN scenario, which is the last discussion in any war game, that is a CBRN or NBC. So that is also one domain where we should start thinking upon. A dual function material that no current BPJ addresses at this stage. STF liquid is Armour is also one field where a lot of work is happening around in the world. A nano-silica suspension in ethylene glycol impregnated into textile flows freely normally, solidifies when the plastic impact happens. 30% nano-silica loading gives 54.75% more energy absorption. These figures in the green, yellow and blue are the energy absorbed values. Operational significance. You can put STF everywhere. A rigid plate cannot go. Collar, groin, deltoid joints, etc. This is the engineering answer to the Ukraine coverage lesson that I brought out. Nature solved a version of this problem million years ago. Let me show what it found. Nature has been running an Armour research program to 500 million years. And the question is whether we are intelligent enough to copy it. Fish scale architecture, overlapping silicon carbide plus organoplastic composites, scale on a grooved base, and the FE validation has already taken place. The capability it unlocks are flexible, conformal, multi-hit protection for shoulder, sides, and abdominal areas where rigid SAPI plates cannot go. Additive manufacturing we have already covered a lot into the earlier sessions, but there is a requirement that was also brought out by one of the panelists in earlier sessions, that we have to have the logistic revolution in additive manufacturing. The traditional ceramic armor is manufactured centrally, shifted to forward areas or transferred to forward areas of operation, and when damaged is irreplaceable in the field. Additive manufacturing changes this entirely. Silicon carbide, alumina, and boron carbide are now printable. The operational Sindoor lesson is direct. Emergency procurement takes months. A core level or maybe at the command level, additive manufacturing facility producing replacement SAPI plates insert on demand eliminates that dependency. Multi-domain dividend. One investment in advanced composite material pays across 4 domains simultaneously. The graphene reinforced polymer for a BPJ backing is same material which is used for UAV frames, where one of the industry is working, which I came to know. The ceramic composite for WAP vehicle armor is the base for naval hull base. So this is the argument for a dedicated armored forces material research center, which is precisely what the CME can do. Let me now connect for all of this what India has already built. We have gone a long way. India's indigenous armor story is not a story of absence. It is a story of delayed acceleration, and the acceleration is now visibly imminent or underway. Abhed. This Abhed stands for Advanced Ballistic for High Energy Defeat. Boron carbide ceramic plus polymer matrix developed at the DRDO Industry Academia Center of Excellence at IIT Delhi. Weight is 8.2 to 9.5 kg for different BIS levels within GSQR limit. Modular design, front, rear, and additional panels. TOT23 Indian Industries. This is no longer a laboratory result. It is transitioning to a manufacturing reality. Kanchan. Kanchan was from DMRL and India's answer to Cobham British architecture. Ceramic tiles sandwiched between composite panels and RHA. In service since 2004, Mark 1 Alpha adds ERA to the frontal arc. 118 of them has already been ordered. Indigenous content up to 41 to 54%. And beyond Arjun, the future MBT program post 2030 is already in engineering with AI integrated, active protection, and ceramic ERA hybrid configuration. SMPP and BIS ecosystem. And it is very heartening to know that we have developed our BIS for all these protection systems. In 2009, a declared requirement of 3.5 lakh BPJ and zero procurement. By 218, the first Make in India contract was placed. By 2024, Abhed is ready. By 2025, post-op Sindoor, emergency contract are issued. IS 17051 of 2018 means the now define our requirement and threat levels, licensing rather than licensing the same to American NIJ standards. Several countries have already approached India for supply of these BJP jackets. The direction of travel is unmistakable. But who actually manufactures? And now we have seen a few of the industries here. Let me show you the industrial spine of our country. Rana Kali was one of the program where the combined, which has proven the combat scenario. Titanium alloy plus ceramic plus polymer, designed for Lancer helicopter and Mi-17 1V. Protection against 7.62 mm ball and AP, 12.7 mm AP. This armor has received and withstood actual attack in service. That is not a trials result, that is a combat endorsement. Technology transfer to Midhani, the light combat helicopter variant is in development. WAP 8x8, the newest milestone. November 2025, technology transfer to NTB International Pune and QMI covers the CUMI, covers the entire manufacturing chain, zirconia, toughened aluminum, sandwiched with rubber and metallic backing. Stanag 4569 level 2 and 3, defeat 14.5 mm AP rounds and RPGs, 300 unique ceramic panels per vehicle. Production has commenced, and this is not a future program, it is a production reality. Jackal is a DMRL. The DMRL, I would say, is the material spine of India's armor program. And 3 decades of R&D, over 40,000 tons of armor produced. The transfer model that Jackal Steel to SAIL and Midhani is a successful model that has now embraced WAP ceramic armor to NTB and QMI and Abhed to 3 Indian industries, as I already brought out. The strategic gap, there's still a gap which has already been discussed, but few of them is like, first I would like to flag is the scale of requirement, as already brought out, that is the declared requirement of 10 lakh BPJ, against which only 2.5 lakh has been supplied till now. And the emergency procurement kind of procedure post Operation Sindoor, what we took, is a symptom, not a cure. The cure is a sustained domestic production surge anchored to a clear specification and a funded program pipeline. Second gap is the multi-hit ceramic limitation. Although BIS 6 level of Abhed do have it, but that is for the plate. We do not have for all-round protection. So that multi-hit limitation still do exist. The thermal extremities, what I brought out from Siachen to Thar, is that 90-degree operational envelope of temperature is yet to be breached, and where this is where we can collaborate with the industry, academia, and DRDO with CME. CBRN multifunctional, because we are the joint training services for the CBRN, and we tend to forget about this scenario. Once it will happen, then God only knows. So we have to have our protection system to be tested against CBRN scenario, which is not taking place. So this SCRI stands for Sarvatra Center for Research and Innovation, where I had this small nucleus of research and innovation at a core of engineers in College of Military Engineering. And we have moved a lot way since last 4 years. It was established in 2021. There was a lull period in this COVID. Post that we have accelerated a lot of things. And one of them is Padam Kavach. This is boot anti-mine engineers. We have been talking about the body armor, but the foot is the one where foot on ground has to be there for any kind of success in operation. So, and that foot is having danger from those mines, enemy mines. And boot anti-mine is one. So it was a composite work at SCRI. Composite sole, which attenuates 99% of the initial explosive energy from an anti-personnel ND Mark 1. Correction, NMM 14. Commercially produced by Artisans and is now available in 3 variants. So that is the kind of success we could get through in this. Another one is Sarvatra Kavach, which has been delivered. It is a full body armor suit. And it was, in fact, initiative of one of the Army Officer Major Anup Mishra. Now, the suit is being manufactured by TESL, that is Tata Advanced Systems Limited, and a lot of field formations are giving their orders to that. So that is the second success story, which is in fact 50% lighter and 50% cheaper than the global equivalents. Boot anti-mine testing facility, like one area where I was discussing one of the DRDO scientists now, this domain of boot anti-mine, mine boot I'll call it henceforth, is where no testing facility exists. TBRL has one, and the only one is exists with us, that is at CMA. Now, over the period, what I've seen that since last 3 years, I've been testing a lot of boots of the formations. And there has been a drastic improvement in their quality by doing those results. And we could have achieved this quality now. Around 37,000 has been placed by one of the command recently. And we could have achieved this earlier had there been a testing facility of this kind, because from this kind of test, they improve their design and they come up with better solutions. Like even including a additional Kevlar layer would increase the efficacy of that boot. There are other active research threads what we are undertaking, waste valorization using steel swap, EMI shielding in inbuilt infrastructure in the concrete, that is one protection, and thermal composites and foldable composite joints, for out of which we have been able to make one foldable recce board, 3-man recce board. And third one is like we are collaborating with a lot of research academia and industries, and that triad is the solution to all the problems now. So I'll just wind up by saying that research gaps and what way forward we should have is one, multi-hit ceramic architecture that we should have for all body all-round protection, that multi-hit capability protection system, extreme environment testing already brought out, smart adaptive armor, and STF that activates under ballistic load, a magazine layer that monitors structural integrity in real time, graphene embedded sensor network. The US and EU, European Union have active programs. India's graphene center of expertise at Kerala and CME's nanotechnology mandate give us the institutional base. What we lack is a funded program. Just for the information of the audience, that we have been nominated as Center of Expertise for the nanotechnology, and we are establishing ourselves in that domain. Ceramic additive manufacturing, already spoken about, and supply chain resilience, as I brought out, that we should move these facilities as far forward as possible so that there is no supply chain and logistic hassles. CBR and multifunctional integration already brought out, and this is where we should start working, and we should start doing research on this, and we can provide the testing facility for that. And the last one is the future soldier and exoskeleton integration. The US Army is targeting passive exoskeletons by 2028 and powered warrior suit by 2040. The armor weight budget changes fundamentally when the exoskeleton carries the load. We must begin designing for the exoskeleton integrated soldier now, or our armor will be obsolete on the day it is fielded. 6 priorities, one unifying logic, that India has the material science, the institutions, and the operational urgency. What we need is the coordinated investment and the effort. So I'll conclude by saying that the battles of Ukraine and Operation Sindoor have already written the material science requirement document for the armored forces, and those figures like 77.2% of the casualty fragments, that is the coverage specification. Emergency procurement of 300 crore post of Sindoor, that is a capability gap acknowledgement. A 10 lakh BPJ shortfall, that is a production mandate for the industries. What I have shown you today is that the Indian material science ecosystem has the answer to every single one of those requirements. Boron carbide, our own produced indigenously. The backing, the aramid fiber, the supply chain exists. Ceramic additive manufacturing, DMRL and CUMI have the technology. Nanotechnology, CMEs hold a center of expertise designated for this. And these 5 numbers on to the right side, we have already covered all of them. So in the end, I would like to say that soldier's armor is India's most important composite material, itself is a composite material, soldier's armor. The question before this institution and before the armed forces is not whether we can, we demonstrate, I stand corrected, demonstrated, we have already demonstrated it. The question is how far we can choose to move. Thank you, ladies and gentlemen.